We will start with a simple example and assume that we have a controller and a negative feedback amplifier with an all-pole loop gain. So only poles and no zeros to keep it simple for the moment. In the book, you find all kinds of combinations, also with zeros in the origin or whatever. But here we do only all-pole functions, otherwise it's too complex for the start. So an all-pole loop gain, then you can write, let's say we have already done that. The gain, the source to load transfer, can be written as the product of the asymptotic gain times the Servo function, and all those things can be frequency dependent. So the loop gain can be frequency dependent, the asymptotic gain can be frequency dependent, and of course then also the source to load response is frequency dependent. And we assume that the asymptotic gain in this case just is not depending on frequency, but the loop gain can be written as a DC loop gain with a number of poles. So that can be written in this way. Here we have n poles. So then the Servo function, which is minus the loop gain divided by 1 minus the loop gain, we can just substitute the loop gain in this expression, multiply with the denominator of this expression, and then write it in this way. Now let's study this expression. You see here, there's a coefficient that will be 1 because you multiply all these terms, so 1 will remain, and then you have all kind of terms with s. The lowest coefficient, so the 0 order coefficient of s, will be unity, and the highest order coefficient of s will be s to the power of n divided by the product of all the poles. So there will be 1 minus LDC in it, and this is what we are going to take out of the equation. Oh, sorry. So here we have minus LDC divided by 1 minus LDC. So then we have unity, because I told you 1 minus LDC is here. So then we have unity and all kind of terms with s, and the highest coefficient now is s to the power of n, well, minus s to the power of n, of course, with divided by the product of all the poles. But since we took 1 minus LDC out of the equation, we have to multiply it with that. So here you see it. The highest coefficient is 1 minus LDC times the product of all the poles. And this we call the loop gain pulse product. Now, since the DC loop gain is, well, you want to have an accurate amplifier, so you want to have a high DC loop gain. So basically you could say, well, this is negative, yes, so here is plus some large number, so you can usually forget about unity and say only LDC times P, the product of all the poles. Make it a little bit simple. But this is called the loop gain pulse product. So the denominator coefficient of the highest order of S is determined by the loop gain pulse product of the amplifier. Now this is nice, because if all poles are dominant, all poles in this expression, if they are dominant, then this term, knowing the properties of this MFM that I showed you before, this term is omega n to the power of n. So we can find omega n is the nth order root of the loop gain pulse product of the nth order. Which means that we can, usually we have a requirement for the bandwidth of our feedback amplifier, which is the bandwidth of the Servo function as we defined. And from this, we find a requirement for the loop gain pulse product, in which, of course, contributions of the controller can be found, and contributions of other things like lambda, beta, kappa. So basically, you could say the achievable bandwidth of a negative feedback amplifier is the nth order root of its nth order loop gain pulse product.